Hi, today I'm going to talk about satellite contamination in astronomical images, and particularly satellite contamination as a foreground for telescope surveys that are looking for rapidly changing things in the sky, so phenomena on timescales of minutes or less. When we talk about satellites in images, there are really two morphologies, streaks and glints. Streaks like this one are caused by satellites that are uniformly illuminated, so things that are moving quickly across the sky relative to their rotation speed. And if you switch that around, so you have something moving slowly across the sky or rotating really rapidly, what you see is a brief high contrast flash called a glint that can last as little as a fraction of a second. And what you end up observing with your telescope then looks indistinguishable from a star, which is a problem if you're trying to find astronomical events that are happening on similar timescales. So there are a few questions that follow pretty naturally about this population. How common are satellite glints? How bright are they? And what's their distribution look like on the sky? We tried to answer these questions with the Everyscopes, which are these odd-looking all-sky instruments made up of 24 small telescopes ranged across a fiberglass hemisphere. Between the two sites at Mount Laguna, California in the north, and Cerro Tololo in the south, we're able to take a high-resolution image of 40% of the sky every 2 minutes. On top of the Everyscopes, we built a low-latency detection pipeline, which can monitor the whole 16,000 square degree field of view for variable sources in real time, with alerts typically coming out for each image before the next image is even written to disk. The primary science targets for this pipeline are things like this over here on the right, which is the detection of a 100 times flux increase during a large flare from an M dwarf, shown as a film strip of reference, science, and difference images, where the reference and science images are just images of the same part of the sky a few minutes apart. However, in front of events like this, we see hundreds of thousands of single image candidates that are indistinguishable from star-like transients. One clue about what these single image detections are comes from looking at groups of them over time. So on the bottom plot here, you can see small cutouts from those consecutive images, along with the difference between them. Each individual detection is nicely point-like, but over an hour or so, they form a track across the sky, which is consistent with the kind of motion you would see from something in Earth orbit. Based on the length of this track and the time span between the first and last images, you can work out that the angular speed of the satellite is something like 10 arc seconds per second. And from that, we can say the duration of each flash must be much less than 1 second, because if the duration was longer than that, you would expect streaks, that you can see here for these objects that are moving at similar speeds. This is consistent with previous studies that have done time-resolved observations of satellite glints using the Mini Megatortora and WFAST instruments, finding typical durations of less than half a second. Under the assumption that the single image flashes are dominated by satellite glints, we then measure their rates by accounting for the completeness and coverage of our survey. The left side plot here shows the cumulative distribution of satellite glints measured by every scope as a function of magnitude, showing that these events are extremely common with an apparent rate of 1800 per hour. This increases by a little more than a factor of 2 if we limit our analysis to just things that appear around the equator, where the density of satellites is at its highest. On the right here shows the relative magnitude distribution for the same population, indicating that not only are satellite glints common, but they're bright. In fact, they're so bright that many are bright enough to be seen with the unaided eye, though the sub-second durations make it really difficult to actually notice. What measuring these event rates allows us to do is estimate the impact of star-like false alarms from satellite glints, both on our own untargeted survey with the Everyscopes and on follow-up searches for optical counterparts to short-duration transients, like fast radio bursts from CHIME or gamma ray bursts discovered by NASA's Fermi telescope. Ultimately, seeing through this fog of satellite reflections will require mitigation techniques. We're currently prototyping methods to fit orbits to Everyscope detected flashes in near real time, which will hopefully allow us to flag satellite glints in our database. Thanks for watching, and if you have any questions, please feel free to check out our paper on arXiv or in the Astrophysical Journal letters, or just send me an email directly. Thanks again.